Hi everyone, welcome to my video series on numerical linear algebra and optimization. Today I would like to talk about linear transformation, linear function, and affine function, but in the context of matrices. Previously I talked about the affine and linear function for vectors when the domain X is a vector, but today I want to extend this definition to matrices. The X is a still vector, but now we are considering the equation similar to f of x equal to ax, where A is a matrix. And we call this f of x equal to ax linear because it satisfies the superposition principle. Remember, when we talk about the linear functions for vectors, we said f of x equal to A transpose x is linear because it satisfies the superposition principle. Over there, A was a vector. So A was in Rn. Okay. Now, and f of x was a scalar. So if you have not watched the first couple of videos, please go and watch them first. I will put a link in the description. And it helps you a lot to understand the linearity concept when it's extended to the matrices. Now, here, this f of x equal to ax, this A is n by n matrix, and this x is n by 1. So f of x is n by 1 vector, right? And f of xi, or f of x, the ith component, is actually equal to the ith row of A dot product with the vector x, right? So it's a dot product of AI, I call it the ith row of A, and x. This is the ith row of A. Ith row of A, and this is so each component is very similar to this case that we considered before. All right, so let's see why f of x equal to ax versus linear. Remember, we proved this case for the vector, f of x is equal to A transpose x. Now let's prove it for this case. So first, always when you want to prove when something is linear, it must satisfy the superposition principle. Okay, so this is an if and only if statement. Means that if f of x is equal to ax, then it's a linear, and if function is linear, then it can be written as a linear transformation by a matrix. Okay, good. So in order to check why f of x equal to ax is linear, we have to check this condition. I will call it equation 1 here. So let's do that. We set f of x equal to ax. We check this. X, remember, we have to replace x by this quantity, alpha x plus beta y. Okay, now we're gonna go ahead and use the distribution property. And this alpha and beta are a scalar. Last video I talked about the matrix vector product and its properties. We talked about the multiplication by a scalar. So you can take a scalar out and you will get alpha ax plus beta ay. Well, what is ax is nothing but f of x, and what is ay is nothing but f of y. So we get alpha f of x plus beta f of y. Okay, but this is exactly the superposition principle I had in equation 1. Therefore, f of x equal to ax satisfies the superposition principle, and therefore it's a linear function. Okay, so from now on, anytime you hear a linear function, you can consider as a linear transformation by some sort of matrix A. Okay, good. Now, as I said here, the converse also is correct. Any linear function can be written as f of x equal to ax. Let's see why this is correct. So we set x, which is a vector, this vector x, which is n by 1 vector. We talked about that when we were talking about the vectors in the first couple of videos, that any vector can be written as a linear combination of unit vectors. This E1, E2, En are unit vectors, right? Remember, Ei is equal to this unit vector 0, 0, 0, 1, 0, 0, 0, where 1 is in the ith position. Okay, good. So E1 has 1 only in the first position, the rest of the elements is 0. E2 has the 1 in the second position, and the rest of the elements are 0, and then so on and so forth. So x can be written as x1 e1 plus x2 e2 plus all the way to xn en. Where is x's, this x1, x2, and xn are scalars. Okay. Now let's apply this superposition principle, because guess what? We know that this f of x is linear. We want to prove that it can be written as matrix vector product. So we let x to be this, we apply f of x to this, and now remember that according to the superposition principle, this xi's are this alpha and beta, and what we can do, we can actually write it based on what we see in equation 1. So we get x1 f of e1 plus x2 f of e2 all the way to xn f of e. Yeah. If you want to see this one better, I can carry this computation here. It's like this. xn en, and this one is simply f of e1 x2 f of e2 and all the way to xn f of en. Okay, good. Now you let x to be this vector x1 x2 xn, and then you let matrix A to be this f of e1 f of e2. What are these f of e1? These are the columns of matrix A. So according to the notation that we had in the previous video, this become A1, this become A2, and this become AN, because we have n columns, right? So what I mean by that, A is like this. What I mean by that is A is like this. F of E1, this is the first column. F of E2, this is the second column. And F of En, this is the n column. Okay, so we proved that if a function is linear, we can write it as a matrix vector product. It's a very important property. Okay. Now let's talk about affine function. Okay, so the idea is the same as a vector. We just extend this idea to the matrices. Now, the same relationship as we had in a vector, it must satisfy the superposition principle. F of alpha x plus beta y should be equal to alpha f of x plus beta of y, and the sum of alpha plus beta should be equal to 1. So for linearity, we don't have any constraint on the coefficients. For the affinity, we need the sum of the coefficient to be equal to 1. And also another way is that you write it as f of x to be equal to ax plus b. Right, that's another way. So any function that can be written as ax plus b is an affine function. Now to see this one, you know that any x can be written as a linear combination of the unit vectors. So x, you can write it as this x1 e1, we saw that above, x2 e2 all the way to xn en. And you just go ahead and instead of x, let's call this one equation 3, and instead of x, you plug x1 e1 x2 e2 all the way to xn en. And so what is f of x though? F of x is ax plus b. Just plug this x instead of here in equation 3, and then just multiply it out, you get this expression. Okay. But now wait, we want this one to be equal to what? We want this one to be equal to alpha 1 times f of x1 plus alpha 2 times f of x2 plus all the way to alpha n times f of xn. So this is this alpha 1 times f of x1 plus alpha 2 times f of xn all the way to alpha n times f of xn. If you do that and match the corresponding terms, you see that alpha 1 f of x, alpha 1 ax1 is the same in both of them. Alpha 2 ax2 is the same in both of them. What is a condition for these two to be the same is that the b here should be equal to this alpha b plus alpha 2b all the way to alpha nb. That's what I have here. And the condition for that is that alpha 1 plus alpha 2 all the way to alpha n is equal to 1. So that's the constraint for affinity. We have an affine function if we satisfy the superposition principle and the sum of the coefficient is equal to 1. Okay, great. Now we have an interesting way to find this matrix A and B, vector B and matrix A. So what we do is that when you have f of x equal to ax plus b, right, set x to be 0. If x is 0, a times 0 is 0. So we get b equal to f of 0. Okay, so b is equal to f of 0. That's what I have here. Now, to get the first column of A, what do? Set the x to be the unit vector, the first unit vector, e1. What is E1 to remind you? What is E1? E1 is this. Okay. Now, what does it give you? A times E1. Remember we talked about the concept of matrix vector product, and I told you that matrix vector product is equal to linear combination of columns of a matrix. This is the same thing. AE1 is this, 1 times A1. A1 is the first column of A, plus 0 times A2, all the way to 0 times AN. We have n columns. So it gives you the first column of A. This is the first column of A. That's what I wrote here, plus B, right? So f of E1 minus B gives you the first column of A. But what is B? B is just f of 0. So this is going to be the first column of A. This is going to be the second column of A, and all of it is going to be the last column of A. So this is going to be matrix A. Okay? So that's a nice way to find them, all the elements of matrix A when you have a affine function. Okay. Now let's move to the geometric transformation. Geometric transformation of a linear function. Right. So when you have a y equal to ax, depending on what is this matrix A, you can have different form of linear transformation. Now, if A is equal to a scalar A times an identity matrix, what do I mean by that? So remember the definition of identity matrix is this. Okay, and this scalar A like can be 2, 3, 4, -1, -2, right? We want to see what happens if A is equal to a little a times identity matrix. We call this sort of transformation the scaling. Why do we call it the scaling? Why do we call it scaling? If you multiply the identity by x1, by x, what do you get? Well, what we get is just the x back. So in this case, the little a is equal to 1. And we are not really changing anything for the vector x. This means that we scale it by factor 1. We haven't done anything. Now assume the absolute value of a is greater than 1, right? What will happen is that, let's say a is 4, right? It means that this, we have this one here, 4 here. If a is 4, right? This means that we multiply every component of x by 4. Therefore, we multiply the whole vector x by 4. So we actually scale the vector x by 4, right? So in general, if a is equal to ai, then y equal to ax, y is equal to ax here, little a, right? So we are scaling component of x, but all the components with the same amount, right? So x1 by a, x2 by a. So it's the same thing that we talk about that in the context of vectors. You are multiplying a scalar by every single element of vector x. We call it a stretching. If the a absolute value of a is greater than 1, you're a stretching vector, right? So for example, nice example in 1D would be this. If you have a vector like this, and if you stretch it by a factor of 2, you might get like this, for example, the same direction. If absolute value of a is less than 1, you are shrinking them. So this is the case of a stretch. And for shrinking, let's say by 0.5, you get this, you get shrink. Okay, let's say for a is 0.5. Now, if a is less than 0, we are actually flipping the vector. We're reversing the direction of vector. What it means is that, let me use another color. So you get this, for example, a less than 0, reversing direction. Okay, good. Now, the question here arises that what if we want to scale different elements of a vector by different number, by different factor? No problem. Remember this, we have this identity, right? Element on the main diagonal was all 1. What if I have a general diagonal matrix? Remember this notation that we used? We defined that in the previous videos. This means this A1, A2, all the way to AN, and you have 0. So now if you go ahead and multiply this one by a vector x, perhaps it would be better if I set only this one A. What you get is what I have here. y1 is equal to a1 x1, y2 is equal to a2 x2, and yn is equal to an xn. And these numbers can be different. For example, a1 can be 1. An example of this is a1 can be 1, and then we have 0, 0. A2 can be, I don't know, 2, 0, 0, and A3 can be 3. So we scale the first component of x by 1. We are not changing that. The second one, we change it, we multiply by 2. We scale it by 2 with the same direction, of course, because A is positive. And then the third component, we scale it by 3. So this is called dilation sometimes. But let's consider as a scaling with different factor, multiple different elements of x by different factor. This is general version of identity matrix. So remember we talked about this diagonal matrix. The diagonal matrix in general is say identity matrix is a special version of a diagonal matrix, where the elements on the main diagonal or all these AIs is equal to 1. Good. Let's move to rotation. This is important. What if we want to rotate the vector x by angle theta counterclockwise? So if we have our unit circle here, counterclockwise means this, right? This is counterclockwise. Then the rotation matrix, which is a very famous matrix, is cosine of theta, negative sine of theta, sine of theta, and cosine of theta. Okay, so for example, if you want to rotate it by 30 degree counterclockwise, this A becomes what? This A becomes root 3 over 2, negative 1/2. You just plug 30 for theta. 1/2 and root 3 over 2. Okay. Now, what if you want to rotate it by theta clockwise? All you have to do is change the theta to negative theta. If theta is going counterclockwise, negative theta is going clockwise. So what you get here, just change the theta to negative theta. Cosine is an even function. Negative theta and theta are the same. So you get cosine of theta. Sine of negative sine of negative theta. Sine is an odd function. This becomes sine of theta, negative sine of theta, and cosine of theta. Okay, good. Let's talk about reflection, right? What happens if you reflect a vector about the x-axis, right? So this is a diagram I have here. This is our vector here. This is our point in 2D. You can also draw this vector here if you want. So what would happen here if you reflect it around the x-axis? I get the new point here. This point will have the same x, but the y component will multiply by -1, right? So let's see how you get the matrix A corresponding to this linear transformation. You will write the new point here. This is the new point. What is this new point? Is x1 negative x2. And then you will ask yourself what matrix I should multiply by the original vector I have, x1, x2, to get this new point. So let's see. The first component is the same. So 1 times x1 times plus 0 times x2. You get x1. And then 0 times x1 is 0. Negative 1 times x2 is negative x2. So this is the matrix A. 1, 0, 0, 1, 0, 0, negative 1. This is the matrix corresponding to reflection about the x-axis. Now, what if you want to reflect about the y-axis? No problem. This is the original point. Original point. Reflection around the y-axis, or here we have x2 axis, x1, x2. This means that the y component are the same, and the x component will be multiplied by -1. So now this is a new point. This is a new point. I read it from here. New point is equal to this matrix A that I have, -1, 0, 0, 1 times x1, x2. Okay, good. So this is called reflection about the y-axis. Okay, so we have some famous linear transformation, scaling by constant number, scaling by different factor for different component, rotation, and the reflection. Now you can combine them. You can say that what if, hey, I want to first reflect that about the x-axis, and then I want to rotate it by 30 degrees. Then I want to scale each element by different factor. Well, let's say A1, A2, let's say case in 2D, or A1 and A2. What would happen in that case is that you have your vector x1, x2. First, you want to rotate it, no problem. You just multiply cosine of theta, negative sine of theta, sine of theta, assume counterclockwise, cosine of theta. Then you want to go ahead and reflect it, I don't know, about the x-axis, 1, 0. After all, it's a linear transformation, so it's just a matrix product. And then what I want to do, I want to multiply the first component, I want to scale it by 2, but the second component, I want to flip the direction and then multiply by 4, so negative 4. So that's what's going to happen. Okay, and then you can come up with different permutation of this scaling, reflection, and rotation. The next concept is Taylor approximation. We talked about the Taylor approximation for the vectors when the domain was a vector and the codomain was a scalar. So the function f, we talked about that when the function f was this. F was a scalar. The codomain of f was a scalar, right? Now we extend it to the vectors. So the point x and the point that we consider near the point x, z, they are vectors and dimensional vector, but the function f will be vector as well. Okay, let's see how to define this. So first we have to define function f to be differentiable with the partial derivatives defined, because we want to eventually take a partial derivative, so they must be defined. And the z is an n-dimensional vector. So assume this z is any point close to x, right? We want to find the Taylor approximation of the function f of x, right, near the point z. Okay, what we are going to do is the same thing that we had for the case of vectors. Now here our x is n-dimensional and our z of course is n-dimensional, but the function f has m components. What it means is this. So it's this f of x1, the first component, f of x2, the second component, sorry, f of x, not f of x1, f of x here, and all the way to f of x, m component. So I'm saying that take the ith component, the ith row of this, the ith row. It's defined very similarly to the vector case. We have f of iz, right? The ith component manually calculated at the point z, plus now this partial derivative, right? When you calculate the round of f of iz, calculate z based on x1. When you calculate this derivative based on x1, the first component of x, and you multiply x1 minus z1, right? It's very similar to what we had in the case of vectors. Now this is partial derivative because we can take a derivative with respect to different components. So when you take a derivative with respect to x1, the x2, x3, all the way to xn are considered as constant, right? Plus all the way to f of I, manipulate as z, take a derivative with respect to x of n, right? Multiply x of n minus cn. Now, when you look at this equation, of course you write this one here, f of iz, but when you look at this reminds us dot product, right? Remember we defined dot product A transpose B to be this, AI BI, right? Means A1 B1 plus A2 B2 all the way to AN BN. This is very similar. We're just multiplying two quantities and add them up, right? So this is gonna be a dot product of what? It's gonna be dot product of partial or gradient of f of iz trans or f of iz and x minus z, which in dot product you can write it like this as well. Now you have to define this term. So first, as I said, x and z are n-dimensional. So x, the components are x1, x2 all the way to xn, z, z1, z2 all the way to cn. And what will happen is that, remember f of x was m-dimensional. So for f of x, we have this, I defined it before. This hat means that we are estimating this function. is equal to this. This is equivalent of this. If you collect them all together, this component, so for you might get one f of z, one f of 2z, all the way to f of mz, not n, mz, because I is changing from 1 to m. Right? If you put them in a vector, you get this f of 1z, f of 2z, all the way to f of mz. And this vector also is very easy. This vector x minus z, just go ahead and subtract these two vectors from each other, right? Component points, we define the subtraction of the vectors, right? x1 minus z1, x2 minus z2. So this is easy too. Well, what is this matrix? It's a very, very important matrix used extensively everywhere for a change of coordinates and to actually change the domain of a problem. Sometimes a classification problem, regression problem, sometimes the problem is hard in one domain. You move it from Cartesian coordinate system to the polar to a spherical coordinate system. So this matrix is called Jacobian. Let's see what are the elements of Jacobian matrix. So what's the first row of Jacobian matrix? The first row. The first row of this Jacobian matrix is the partial derivative f of 1. F of what is f of 1? Is the first element, the first component of f, this one. Remember, f after all is a vector. So f of x itself is this. Right? The first component, f1 of the first component, the partial derivative f1 respect to x1. What is x1? The first element of x. So x is n-dimensional, right? And f is m-dimensional. Let's look at the dimension here. This one is n by 1. This one is m by n. Why is m by n? We have m rows. Each row corresponds to the derivative of ith component of f, right? The second row is going to be partial derivative f2 respect to x1, the first one, then respect to x2, then respect to all the way to xn. So we have n columns. The number of columns determine the number of elements in a variable x here. The number of rows determine the number of elements in a function f, right? So what is the mth row? The mth row is a partial derivative of f of m, the mth element of f. The first one is f of m respect to x1, then x2, all the way to xn. This one is Jacobian matrix. It's a very famous and important matrix. So this is the extension of Taylor approximation to the case of matrices, and then f is not a scalar, it's actually a vector. Okay. So you can actually write this one in a more compact form as follows, like this f of x. This f of x is this one, I define it here. This f of x, this is called f of x, is equal to f of z. This is f of z, right? Now, is equal to this d times f of z. This d times f of z is called Jacobian, right? This d operator is the Jacobian operator. Usually d operator is used for a differentiation operator. This capital D is for a Jacobian operator. So df of z is this. So df of z is this one. And then you call x minus z as your new x, as new vector x, capital X, right? So this one is a vector, and this this one is a Jacobian matrix. This one, the entire df of z is a Jacobian matrix, right? Which here I define that what is each element of df of z, ij, each element, each ij element is equal to partial derivative of f of I respect to xj. Right? Remember, the columns are for the variable, the rows are for the function, and that's why the I goes for f and j goes for the variable. I is changing from 1 to m because function is m-dimensional. J is going from 1 to n because the variable is n-dimensional. Now, so what is this function? Let's take a look at that. This function f x can be written as what? It can be written as ax plus b. Right? Where a is this df of z, and b is this f of z, and this x is our capital X that we had there, right? So this is called affine function. This is just an example of affine function, that I defined before. Okay, it's a very famous example of affine function. Now let's talk about system of linear equation. So here I want to just introduce you to some concepts. We are not really solving any linear equation here. We've solved linear equation after we discuss about inverses in the next videos. So first we need to define some concepts to be familiar with certain terminologies, then we will define the inverses, and then we jump into solving system of linear equation. So right now we are not ready for a linear equation. So consider we have m equation, linear equation, with n variables, x1, x2, all the way to xn. So you can express them like this. a1, 1x1, a1, 2x2, and these are like coefficient is equal to b1. So these bi's is usually called the right-hand side of equation, these bi's. And these aij's are called the coefficients. If you write this as like a system of equation in a matrix form, you get this one in the form of ax equal to b, which a as an element like this, a11, a12, all the way to a1n, and then all the way am1, amn. And the b, b1, b2, all the way to bn. So, and then this matrix that we have here is a matrix of m by n, right? So you see it here, there's m rows and there's n columns. So this is m by n matrix. So you can write any system of linear equation in a matrix form ax equal to b. Now, a set of linear equation can either have no solution, one solution, or multiple solutions, right? So this is an important concept to know for now. After we talk about the knowledge spaces, then we will see what happens if we have multiple solutions. And then we will talk about under what condition we have a unique solution. We need to talk about the inverses, and then under what condition we never have any solution. Now let's talk about certain terminologies. I defined them before. What's the definition of a tall matrix? A tall matrix is a matrix that it has more equations than variables. Now we can define it in terms of linear equations, right? A tall matrix is a matrix that has more number of rows than number of columns. M is greater than n. So like, for example, this is an example of a tall matrix, right? Remember, each of these rows correspond to equation. For example, I wrote it here, I've written it here. x1 plus x2 is equal to 0. So this multiply this, and 0 is this. x1, 1 times x1 plus 0 times x2 is equal to 1. 0 times x1 plus 1 times x2 is equal to 1, right? So we have three equations. So rows of matrix correspond to number of equations, columns correspond to number of variables, and two unknowns, right? So a tall matrix might not have any solution. So for example, in this case, we didn't have any solution. Why? So from here, if you add these two, let's call equation 1 and equation 2, if you add them up, you get x1 plus x2 equal to 2. Well, wait, equation, so let's call this one 1, and this one 2, and this one 3. Equation 2 and 3, when you add them up, you get x1 plus x2 equal to 2. But wait, equation 1 says x1 plus x2 is 0. So this one has no solution. So a tall matrix might not have any solution. This type of matrix is called, this type of linear equation is called overdetermined system of equations. Overdetermined means we have more equations than variables. So this is also called as overdetermined system of linear equations. Now let's talk about A is wide. If A is wide, right, means that we have more variables than equations. More variable than equation, right? So for example, here x1 plus x2 is equal to 1, x1 plus x3 is equal to -1. Hey, we have three variables and two equations. So one of the variables is free variable. It can be anything, right? So there is, as I wrote here, there is a solution for x1 and x2 for any choice of x3. So here we call x3 as a free variable. So this has a multiple solutions. So a wide matrix can have multiple solutions. Okay. Well, Now, when you have a square, means that same number of variable is equal to number of equations, right? And you have a independent columns here, then you have a unique solution, right? So in this case, when you have a square with independent columns, then you have a unique solution. For example, here you have x1 plus x2 is 1 and x2 is 0. So x1 must be 1. Okay. So now this is the definition of stuff I just talked about, that overdetermined is tall matrix. The number of variables is more than the number of equations is more than number of variables. Void means m is less than n. Number of rows is less than number of columns. So we have more variables than the number of equations. So always remember this. Visualize this one. We have a free variable. So we can have infinite many solutions. And then, of course, with a square, we have same number of variables as equations. Now, there is another term that I want to define is the homogeneous equation. It's defined when the right-hand side, remember the right-hand side was the vector b's, right, is equal to 0, right? This means that b1 equal to b2 all the way to equal to bn equal to 0. This is a term that shows up a lot in the literature. So we have a name for the homogeneous system of linear equation when ax equal to 0. Okay, so that's it for this video. In the next video, I'm going to talk about the inverse, matrix inverse, left and right inverses, properties of inverse, and the pseudo inverse. Thank you so much all for watching. See you all in the next video.